Hello and welcome to the chapter on equilibrium. If you survive last chapter, you'll do fine for the rest of the class. Last chapter is really hard with kinetics. This chapter is much easier. So we've got the equilibrium, and although the rate is important, right now all we really care about is that the forward rate equals the reverse rate. So, and equilibrium, it's kind of one of those things it looks like nothing is happening. But there's actually a dynamic equilibrium. Things are still going back and forth, but the forward rate equals the reverse rate. It's kind of like balancing. Like when you stand up straight, you think, oh, I'm just balancing right now. But actually, there's a lot of little muscles going on. Your feet, your ankles. You have to think about staying up straight. It takes some effort to stand up straight. Of course, if you tranquilize someone, that person falls over immediately because they lose the ability to think and concentrate about it. So it's actually hard to balance yourself. We require quite a bit of brain power to do that. Likewise, chemical reactions, even though it looks like everything's balanced, it turns out that they're on the molecular atomic level. It's teeming with activity. So let's look at here as an equilibrium. Hemoglobin plus oxygen makes oxygenated hemoglobin, and the forward rate equals the reverse rate. So this is partially true. So there's actually 4 oxygens that attach to each hemoglobin molecule. There's 4 heme groups, and it's arranged such that it's easier to keep it oxygenated. So we can gather up oxygen very quickly their bodies. But in a fetus, there is a slightly higher absorption ratio of oxygen. So that's how the oxygen is able to travel through the placenta then to the unborn child there. So, and there's other examples in hemoglobin. So how we get oxygen to our bodies, our blood gets oxygenated in our lungs, right? And then the oxygen attaches to the hemoglobin, and then the oxygen will detach and then go to our cells. The way we get carbon dioxide is we exhale. And also, carbon dioxide dissolves in our bloodstream to form carbonic acid, H2CO3, and we can exhale that. And it's a reversible process. There's other chemical reactions like hydrogen and iodine making 2 hydrogen iodides. These can go forward and reverse directions. And let's look at this here with hydrogen and iodine. So here on the bottom part of the graph, you have concentration on the y-axis, and you can see hydrogen on the top, iodine on the top, and then hydrogen iodide coming up from the bottom. And as the reaction progresses, the hydrogen iodine decreases, the hydrogen iodide increases, and then you get to a point where the concentrations don't change. Although nothing is changing macroscopically, microscopically it is changing. And that's the dynamic equilibrium. And these pictures here show that even though it looks like the overall process is changing, they're still going back and forth. And another analogy would be with immigration. So if there was country A, country B, country A is overpopulated, B is underpopulated. When the borders open up, then suddenly a bunch of people move, but eventually the population will equilibrate. The number of people leaving will be the number of people arriving. So that's an ideal world, of course. The politics may change, as we've found out. Okay, so here is my most general chemical reaction. Little a of A, little b of B, an equilibrium with little c of C and little d of D. The equilibrium constant is the concentration of the products raised to their stoichiometric ratios at equilibrium over the reactants at equilibrium raised to their stoichiometric ratios as well. And again, the brackets means concentration of moles per liter. And it's products over reactants. So this will come important later. We talk about things. So let's just start out by simply writing it. What is the equilibrium constant for methanol and equilibrium with carbon monoxide and 2 hydrogens? So it's products, your KEQ, it's products. It's going to be CO at equilibrium. Hydrogen at equilibrium squared from the 2 over methanol. CH3OH. Like that. Pretty easy to write. So let's talk about this. Let's talk about the size of K. And K is the products over the reactants raised to their stoichiometric ratios. If K is really tiny, so if a really, or yeah, K is really, really tiny, that means that the reaction does not proceed very far. So an example of a reaction that does not proceed very far is what's written down there. Nitrogen plus oxygen makes 2 nitrogen monoxide. In this atmosphere, it's 78% nitrogen and 20.5% oxygen, discounting water vapor, of course, so in dry air. There's quite a bit of nitrogen and oxygen, but there's not too much nitrogen monoxide. That's because this reaction doesn't proceed very far. And if if K is about 1, the reaction proceeds about halfway. If K is a huge number, that means that products are big and reactants are tiny. That means the products are favored. So hydrogen plus bromine make an HBr. That's an example of a reaction that proceeds very far. Let's look at this one. At a certain temperature, the ammonia synthesis reaction, 3 hydrogens plus nitrogen makes 2 ammonias, is 0.95. So therefore, at this temperature, the reaction, what should I say? This one goes about halfway. It's close to 1. So 0.95 is close to 1. And in general, so if it's around a factor of 1,000, if it's 1,000th to 1,000, you're going to see both reactants and products in equilibrium mixture. So relationships with the equilibrium constant. If you reverse the equation, you invert the equilibrium constant. So if A is going to B, the K is products over reactants. If you switch the equation, B, which was a product, is not a reactant, going to A, it's going to flip the equilibrium constant. If you multiply the equation by some factor, you raise equilibrium constant to that factor. So if you have A in equilibrium with B, and then N of A of N of B, that's going to be the equilibrium constant raised to that N power. And for multiple step reactions, use the overall reaction for equilibrium constant. So if there's A in equilibrium with an intermediate, the intermediate goes to a product, and the overall reaction, just ignore the intermediates and go for the overall. So let's apply this. Why would you want to apply this? So because of Excel or other spreadsheets, if you're tracking something, if you're tracking a chemical reactant, it's easiest just to calculate it outright. And this is how you do that. So I'm looking at nitrogen ammonia synthesis, and I want to figure out what the concentration, what the constant is in respect to nitrogen. Oh, no, sorry, to ammonia. So when we look at this, what are we doing? We've inverted the we've flipped the chemical reaction, and we've also multiplied by 1/2. So that means that in this, our new prime is going to be 1 over the equilibrium constant square root of that. So this is going to be 1 over the square root of 3.7 times 10 to the 8th. So put in my calculator. 1 divided by 3.7 E8 to the 1/2 power. And this is 5.2 times 10 to the minus 5. So now we have our new equation there. So, okay, but that's pretty straightforward. Now let's change topics. We've talked about K. What I really meant is Kc, although usually if you see K, it means Kc. Kc is the equilibrium constant with respect to concentration. There's also Kp, that's the equilibrium constant with respect to pressure. And K. So if you look at this reaction here, two sulfur trioxides in equilibrium with two sulfur dioxides and oxygen. The Kc is a concentration of the products SO2 squared O2 over SO3 squared. But instead of the concentration, look at the pressure. It's going to be pressure of SO2 squared over pressure O2 over pressure SO3 squared. It's just easier. With gases, a lot of times it's just easier to deal with pressure. So our Kp is going to be the Kc times the quantity RT raised to the delta N. Delta N is the change in the number of moles of gas. It's the final minus the initial. For this reaction, we have final 3 moles of gas, initial 2 moles of gas. 3 minus 2 is 1. So that means the Kp is going to be the Kc times RT to the first power. Or you could say Kc is Kp over RT. Okay, so let's apply this. Nitrogen monoxide can be oxidized to form nitrogen dioxide. What is the Kc for this reaction? So the Kp is equal to 2.2 times 10 to the 12th. So that means our Kc is going to be Kp over RT to the change in N. That's a P. So we have 2 moles in the products and 3 moles of gas in the reactants. 2 minus 3 is minus 1. So this means Kp over RT to the minus 1 equals Kp times RT equals 2.2 times 10 to the 12th times R 0.08206 and liter liter atmosphere over mole Kelvin. And the Kp, the units on this, is going to be, let's see here. So the Kp products, it's going to be 1 over atmospheres, right? So 1 over atmospheres, and then RT temperature 298 Kelvin. And so the Kelvins cancel, the atmospheres cancel, and we're left with that. Let me pause it and calculate it out. Okay, so there is the calculator result, and you can see it's 5.4 times 10 to the 13 is the Kc for this reaction. Okay, so here is one. So hydrogen and iodine reacting to form 2 hydrogen iodides. The Kc is 620. What is the Kp? See if you can figure this out. So the delta N, there's 2 moles of gas on the left, 2 moles of gas on the right, so the delta N is 0. RT to the 0 is just 1. So the Kp is equal to Kc. The answer is A. Okay, so what about if there's a liquid and solid in an equilibrium constant? So for instance here, look at this reaction. 2 carbon monoxide gas is in equilibrium with carbon dioxide gas and solid carbon. So the equilibrium constant is the product CO2 over times concentration of carbon all over the concentration of carbon monoxide squared. What we do is we remove the concentration of the solid and or liquid. The reason for that is because they're constant. Water, for instance, water has a concentration of 55.6 molar. So that's liquid water. And if you have a droplet of water, an ocean of water, a glass of water, does the concentration change? No. It's an intrinsic variable. It's the amount per volume, so it doesn't change. It's like density. That's the density. What's the density of a single chocolate chip or a brick of chocolate or a mountain of chocolate. Is the density going to change? No, it's not. So that doesn't. So it doesn't change. So we remove it from the equilibrium expression. Okay, so pay attention to this because we're going to be using this type of problem and this type of approach for pretty much the next 3 chapters. So, and it's called, colloquially call it the ICE chart, initial change equilibrium. So let's look at this example. Consider this reaction. Carbon monoxide plus 2 hydrogens makes methanol. So the initial concentration of carbon monoxide is half molar, hydrogen is 1 molar. At equilibrium, the concentration is defined to be 0.15 molar. What is the value of the equilibrium constant? So initially, carbon monoxide is going to be 0.5 molar. Initially, hydrogen, it's 1. And not listed, so we assume this is 0. And we also know that the carbon monoxide equilibrium is found to be 0.15. Okay, so what we can infer from this is that the carbon monoxide has dropped by 0.35 molar, right? So if it starts off at a half and comes to 15, we've lost 0.35 molar in that. And notice hydrogen, there's a 2-to-1 ratio, so hydrogen, we're going to lose 0.7 molars of that. And it's because of the 2. And then methanol, we're going to gain 0.35. And that tells us then that hydrogen is going to be 0.3 molar and methanol is going to be 0.35 molar. So the equilibrium constant from this is going to be 0.35 molar all over carbon monoxide 0.15 and then 0.3 squared. And that's a pretty easy one to throw in a concentration. What is the value of the equilibrium constant? I can go ahead and do this while I'm talking to you. And this is 20, how many sig figs? We have 25.9. Okay, it's 30 sig figs. Oh no, you have 2. So 26. And there is our answer. So although I'm done with this section, you will see this initial change equilibrium pop up many, many, many times coming up. Okay, so remember this as we move along.